So it's 3 o'clock. So it's a pleasure to have Jan back to Sweden, and he will tell us everything about topological field physics.
Yeah. First of all, thank you for inviting me here. It's always a pleasure for me to come back to Sweden. It's like my second home. I must say that when Maxime asked me to give a series of lectures, I said yes without thinking too much of what I'm saying yes to. So then I realized that I was quite unequal to the task, because the subject of TFT has been evolved into such a vast subject, and what I'm covering here will be just a very small portion of it. And all of this stuff that I'll be covering here are developed actually in the previous century, and certain stuff actually goes way back to the 1920s. So there'll be no new things in my talk. And so I've divided my lectures into two parts: the non-perturbative part and the perturbative part. And by TFT, in this talk, I will just it's just consignment theory. I will not talk about any other TFT. So first of all, I think for the non-perturbative part, I'll start by reviewing what's TS axioms of topological field theory, which is the theoretical basis for doing computation using surgeries, that is gluing and cutting, and which means I have to tell you about the surgeries on a three-manifold. And actually, I've divided the subject of surgeries into two parts. One is in here, and some more will come in this section, because it's a pretty big subject, and I don't want to tell you more than what is necessary. And after that, I'll tell you what is, just review the basic stuff of quantization of consignment theory. First, the simple cases on a sphere and spheres with punctures. And also, a more weighty subject is how to quantize it on a torus. And then, which means I have to review what is geometric quantization, and also the equivalence determinant line bundle, and also then I'll figure out what's the wave function for consignment theory on a torus. From the wave function, I can figure out what is the S matrix and T matrix. These are the two matrices that generate the SL2Z on a torus. And with this information, I'll be able to compute the partition function on some simple manifold. And also, I'll get the Jones polynomial. And for the perturbative part, I'm not sure if I will get that far, but let me just give you the contents. So I'll just basically do one loop, but one loop is messy enough. It involves lots of ingredients to just get the determinant factor straight. So it involves the eta invariant, and also the Reitmeister Raisinger torsion term. And this torsion turned out to be related to the Alexander polynomial. So I've prepared some fun stuff here. We'll do some calculation with lots of diagrams. And also, I'll tell you about the framings of the three manifolds. Basically, this one are all there just to get the phase of the one loop determinant straight. And this guy is the absolute value of the determinant. And if we still have time left, I'll try to maybe just show you how to do these diagrams without doing any work. Actually, I will show you that these diagrams can be just written as the derivatives of Alexander polynomial, and maybe even to this one. That is, if we have time. So I'll start with the TS axioms of TFT. So let me just remind you a very simple fact in quantum mechanics. So let's say quantum mechanics is just 0 plus one-dimensional QRT. And let's say you have a particle. Let's look at this amplitude. That is a particle starting from position Q0, and in time t, it goes to Q1. And this, as Feynman taught us, can be written as a path integral. So let me just mention that Hamiltonian depends on both momentum and a coordinate. Well, maybe not that one. So this can be written as a path integral as dq so it can be written in a path integral representation like this. So now the integral is over all the paths that starts at q0 and ends at q1. So well, this you recognize as the action for the Lagrange. Well, it should be the Lagrangian. But and in general, if we want to look at the amplitude from an in state to out state, it's just. So it's very simple. We just expand the in state and out state in terms of coordinate basis, and you just get. And well, multiplied by this integral, integrate over. Right, so you basically expand these two states into coordinate basis, and then do this path integral, and then convolute with the Q0 and Q1 integrals. And and this in physics is called the wave function. Now, which means well, since I said QFT is just a zero plus one dimensional. Or QFT, quantum mechanics is 0 plus 1 dimensional QFT. We could just, well, basically by doing QFT on a segment which is 0 to t, and then we can just understand this formalism as saying that the path integral assigns the boundary of this segment, which is the initial and final point, a Hilbert space, while the in state and out state is just a vector in the Hilbert space. And then the path integral gives you a map from this Hilbert space to that one, and let's try to say. And so for our purpose, we will just be interested in a three-dimensional topological field theory, which means we go to 3 dimensions. Well, the same story can be repeated for 2 plus 1 dimension, which means if you have a you're doing QFT on a 2-dimensional Riemann surface times the segment, and then what the path integral does is that it assigns the 2-dimensional surface a Hilbert space, and also the path integral will give you a mapping from a vector in this Hilbert space to the initial state to the final state. So this is just a simple review of quantum mechanics stuff. So now I think I want to erase that. Now let me make a table of Atiyah's axioms and what is associated with what in his language. So, this is Atiyah. So for 2-dimensional Riemann surface, Atiyah, or rather TFT, associates a Hilbert space, as we have already seen. And for M, which is 3-dimensional, such that the boundary of M is sigma, the path integral assigns a vector in the Hilbert space. Let me call this Hilbert space H of sigma. And an equivalent way of saying this same thing is that path integral M with fixed boundary condition on sigma it's assigned the wave function. So going from here to here is the same thing as I did earlier by expanding the in-state and out-state into the coordinate basis. And now, what is the analog of evolution? So we need to introduce the notion of Fordism. That is, let's draw something. So a Fordism is just a three-manifold whose boundary is a disjoint union of two-dimensional surfaces. So on this side, it gives you it gives you a map from one of the Hilbert space to the other. And another thing I need is reversing orientation. This goes to Hermitian conjugation.
Can you change the pen?
Yes. Probably it's better if I use the black ones.
Yeah.
And also a special case of this one is the trivial Fordism, which is you just take it to the sigma times a segment. This gives you identity. So in the previous case, when I was dealing with QFT, this was the time evolution. But in topological field theory, the Hamiltonian is always zero. So you get no evolution. That's why it's always an identity. And finally, gluing of two Riemann-manifolds to M and M prime along the common boundary on this side gives the inner product. So let me give this a name. Call it psi M. So it's a vector in the Hilbert space of H of sigma. Okay. So this is the association that's given by Atiyah. I think the analogy is quite clear from the previous QFT example that I gave you. So any questions about this association? Oh, I forgot one thing. I should have turned over the page. Empty manifold. Well, so okay, let me just say this: disjoint union, disjoint union on this side gives you tensor product. And then this association would necessarily tell you that the Hilbert space assigned to an empty two-dimensional surface would be just a complex number, because what I'm doing is that the disjoint union of anything with an empty space is just itself, which means while tensoring with complex number gives you whatever it is you had before. Okay. Oh, I forgot one more thing. So finally, another association is that for three-manifold M, if it's of empty, it's equal to empty, which can be thought of as just a Fordism from empty manifolds to empty manifold. And this is called the partition function. Okay, this is the full list. Okay. So this association actually gives us a way to compute the partition functions. So the strategy will be to, if this is clear, I'm going to erase it. Oh, well, maybe I erase it. So what you will be doing is that for a three-manifold, you hope to just cut it into two pieces. each of which you hope to be under control, and then you glue them together, because we know that gluing 2, 3 manifolds along the common boundary gives you the inner product. So, let me write, if you want to compute partition function on the manifold M, so you write M as write it as the gluing of M1 and M2 along their common boundary sigma, and then, which means I can just write the partition function of this guy as where so both psi M1 and 2 are vectors in the Hilbert space assigned to sigma.
Can I ask a question here that has to do with this orientation? Because when you glue together, is there some sense of orientation here now that corresponds to taking psi star psi when you think of
Yeah,
it?
because so I guess the convention is that if you have a boundary, then you take the outward pointing as the positive orientation. But then when you glue these two together, necessarily one guy will have inward pointing vector. So you really reverse the orientation. That's why you get a complex
So
conjugation.
that's the rule you put into it.
Right.
Oh.
So now, so which means we will be just cutting and gluing 3 manifolds, and for this purpose, I'll make a slight digression to tell you some basic facts about 3 manifolds. So for 3 manifolds. So oriented and closed. So I'll write on the list and I'll comment on each of these later. So they are parallelizable, meaning T of M is always trivial. So the tangent bundle of M is always trivial. Second, they have the so-called Taggart splitting. That is to say, M can always be written as, let me write, where M1, 2 are handle bodies. I'll tell you what is a handle body later. 3. So this is very useful because that tells you that you can always hope to cut things into something quite regular. And they all can be obtained from surgery along a link inside of S3. Finally, all are zero bordant, meaning all of such manifolds are boundary of somebody else. Okay, so let me comment on each of these points. So the first point, their tangent bundle is always trivial. Well, first of all, since I assume that they are oriented, which means they're, well, let me call it B, SO3. So B is the frame bundle, and since I assume that they are oriented, so the structure group can be is SO3. But I would like to so to trivialize this TM, I just need to find a section for this bundle, global section, right? I would like to lift this guy into SU2, which is the spin bundle of SO3. And so it turns out that the obstruction is in W2, which is the second Stiefel-Whitney class. In fact, for three manifold W, all the W's vanish. For these three manifold, all the W's vanish. So there's no obstruction, which means you can always do that. Now, after that, another bit of obstruction theory. That is, the obstruction to constructing a global section lies in the following groups: H1, M, I1, and SU2, and also H2, and I2, SU2. So this is where the obstruction lies. So to see this, let me just briefly comment it, because I don't think it's familiar to all of you. So what you do is that you divide your manifold into cell complexes, and then on the vertices, you just define arbitrarily a section. Okay. Now, because SU2 is connected, you can always extend the section to the to the edges, right? So which means they're all defined here, and so forth. Now, whether or not you can extend this section further into the interior of this 2 simplex depends on whether this guy is 0, because if this one bounds on a trivial cycle in SU2, which actually doesn't have such cycles, then you can't extend it inwardly. But as I just said, this guy is 0, so you can always extend. You can always extend the section inside. Now, the next step will be to extend, it's going to be hard to draw, so to extend it to the 3 simplices, which means you have a section defined on the face of this tetrahedra. You want to extend it inwardly. So again, the same story. If this map bounds a non-trivial 2 cycle in SU2, then you can't extend it. But again, this is 0, which means I can extend it to the entire 3 manifold. And this guy is a principal bundle. So a global section will trivialize it. Okay. So that's the first part. Now, what is Heckard splitting and what is handle body? So a handle body is just really a ball, B3, with a bunch of handles. So it's all filled in, it's solid. And which means any 3 manifold of this type can be written as just gluing of 2 handle bodies along their common boundary. Well, by the way, that boundary is just of Riemann surface of some certain genus. So, right.
How do you glue them?
Sorry?
How do you glue the sigma here?
Sigma is the boundary of this. This is solid, so the boundary is, in this case, is genus 2. Okay. So, yeah. I'll show you some of these gluings in a second.
Sorry, what are restrictions on 3 manifold to have a handle body decomposition?
Oriented and closed.
Just oriented to close.
Right.
No.
Right. In fact, the proof is not that. By the way, I'm just pretending to be very authoritative, but actually I just read these things in a very good book by Licorice. What's his first name anyway? I don't know. I highly recommend this book. It's very reader friendly. The title is called Introduction to North and something. Okay, let me give you an example of how to do these things. Oh no, I haven't commented on this one yet. Right, okay. Let me first give you an example of how to do Heckard splitting on S3. So this requires a bit of mental gymnastics. So let's see. Let me take 2 solid tori. So this space is identified with this space. Now, if I just glue them back to back, like, glue them back to back, what I get is actually two sphere. This comes from gluing this disk with this disk along the boundary, and plus this one is an S1. So this is the trivial gluing I get. Right, actually, I have an exercise for you. So it belongs to this part. So exercise. Find trivialization for T of S2 cross S1. Just pretty simple. So anyway, so if I glue these two solid tori in such trivial manner, I just get S2 cross S1. Or I could glue it. So let me draw this as let me call it this A cycle. Let me call it B cycle and A cycle and B cycle. So if I glue the A cycle, instead of to A, I glue it to B cycle and B cycle to A cycle. And, I just twist it around. The claim is that what I get is exactly a three-sphere. And I don't think it's obvious to all of you, right? So let me try to explain how this goes. So let me just imagine this room being a three-sphere, meaning I put a point at infinity to come back by it. Now, let me just draw a solid tori inside. Now, the complement of, just try to imagine the complement of this solid torus in the room. In fact, you will realize that, let me just draw this cycle here. This is draw this A cycle and B cycle. So this A cycle in this solid torus is contractible, but if you look at it from the point of view of the complement to this solid torus, it's not contractible. While and the B cycle, it's not contractible here, but on the complement it is, which means exactly in this gluing process, A cycle and B cycle are switched, right? So now another exercise for you, part 1. So we know that the solid sphere can be written as this as Z1 squared plus Z2 squared equal to 1, right? So you can, and then let me define U, let me call it T, Z1 squared. Okay, in this way you can think of the three sphere as a as a fibration over the segments, because this guy ranges over 0 to 1, right? Now, if you cut this geometry in between, so on any point that is not on the end, the fiber is actually S1 cross S1, namely a torus. Now, just the exercise that you just, it's a trivial exercise actually. You just look at which of the cycle is contractible to the left and which is contractible to the right, and you will figure out that's probably a more solid way of viewing three sphere as a surgery along the torus. Okay, so actually S3 is very special. Not only can it be split into what, this is a handle body of genus 1, right? So you just attach one handle to it. In fact, three sphere has infinitely many Hegardt splittings with infinitely high genus. So what I'm saying is that you can take a surface with, it's filled in, so you can glue these two together and again get us a 3-sphere. In fact, you can put arbitrarily many holes there, and then the diffeomorphism that's required, it's similar to this one. It's basically so on this guy, this cycle gets mapped to this cycle, and so is this one. So the diffeomorphism is such that this cycle is mapped to that one. Okay. Right, now let me come back to why is it that any these three manifold can be obtained from a surgery along the link in S3. Basically, again, just take any. Am I moving too much?
That's fine.
Just take any three manifold, split it using this Haggard splitting, so you get so each part is just a handle body of a certain genus. Now we know that we can find a diffeomorphism on the boundary of this handle body, such that we can glue them into an S3, but this diffeomorphism may not be extendable into this solid handle body. Okay, so if it can, that means we start out with a S3. Now, the statement being that, the statement is that if you remove enough links from this solid body, you can always extend this diffeomorphism inside, which means what you get in the end is that you glue this one here to here, you get a S3, but with a bunch of links removed. Okay, so this is basically that statement over there, that any three manifold can be obtained from 3-sphere with a bunch of surgeries along these links. The links that you removed are the links along which you do surgeries. Questions? Okay. Okay. Another piece of important surgery that we'll be needing is that how do we get a lens space? So I want to get a lens space. Let me first tell you how to do it using surgery. So it starts out from S3, then you cut out a trivial link, so it's S1. So let me cut out a tubular neighborhood of it, which means I just get a torus, a solid one. And now, okay, let me not show you it. So you have the A cycle, you have the B cycle. Now, by P, comma Q surgery, where P and Q are co-prime, so co-prime. I meant the surgery is such that the PQ surgery is such that after the surgery, the P times A cycle plus Q times B cycle becomes the contractible cycle. Okay. In a minute you will see that this actually makes sense. So.
Sorry, I missed you. You're making surgery of what?
I'm making a surgery of so I remove from S3 a tubular neighborhood of a trivial link.
Yes,
and then so then I put it back with the diffeomorphism, right? And the diffeomorphism is such that the P this cycle becomes okay. No, just several examples. 0-1 surgery. This is actually just the so-called S field, because you see, this means that after the surgery, B cycle is contractible instead of A cycle, because in the beginning, A cycle is a contractible guy. Now, after surgery, B becomes contractible guy, which means what you do is you switch A and B. That's the S2, which in this case, if you do it along S3, you'll get S2 cross S1. Okay. That's nothing. The 1-0 surgery does nothing because what happens is that you just cut it along here and do a 2-pi twist, put it back again, so nothing changes. But this doesn't change the diffeomorphism type of the 3-sphere, but it does change the 2-framing of the 3-manifold. I'll come back to this in the second part of the lecture. Exercise part 2. Again, presents. Okay. So this is a more mathematical definition of length space LPQ. So you start again from S3, which is presented as plus Z2. Then you mod out by a relation. This relation, let me define first psi equals to e to the 2 pi I t. So the pth root of 1. So this relation that you mod out is that Z1, Z2 is same equivalent to Z1 psi, Z2 psi to the cubed power. So you mod out this thing by this relationship, and because I've chosen P and Q to be co-prime, so this action is free. So the quotient is a good manifold, and will turn out to be the length space. And then the exercise is that, again, cut the geometry in two. Figure out that on the left-hand side, what's that right? Okay, just to convince yourself that on the left-hand side, the PA plus QB cycle becomes the contractible cycle on the left side, which is exactly what we have done by using the surgery. And finally, another example is the one plus or minus 1, 1 surgery. This will not change the manifold, the 3-manifold either, yet it has some very interesting consequence. I'll come back to this in a minute. But now let me just make a further comment on the surgeries of 3 manifolds. So you have seen that I said any manifold can be obtained by using surgery along a link, but not all different links not all different surgeries along different links will give you different 3 manifolds. There are certain relations among different surgeries. So
sorry, any 3 manifold you said can be obtained as a surgery along the link?
This is a trivial link. By general, you can have links that, several components. So the statement there is that you can do it on any link, meaning they can be linked. But in fact, you can use these moves that I'm about to introduce so that the links are all discrete. Non-intersecting. Okay, so there are certain moves between these relations of surgeries are called moves. I think they go by many different names. One of them is called the Kirby moves. And let me just introduce one of the very simple move. And so let me have a hot link. So with linking number 1. I think this. Yeah, okay, good. So here on this link, I do an R/S, or I think I call it R, S surgery on this one. Here, I call it, I do a P, Q surgery. And then you can actually combine these two surgeries into a single surgery on this link. Well, you can do it for this one too, but same thing. You can combine these into P minus Q. Well, let me switch notation. So by an R, S surgery, instead of writing that, I will write this R/S surgery. So it only did, well, it's pretty obvious. And when I combine these two surgeries, I can get this one. Notice that R and S are switched here. So, okay. This one, actually I left it as an exercise. Now I'm not sure how wise this is. But so what you do is that, again, you do the same game. You try to figure out who is the contractible cycle in the beginning, who becomes contractible cycle in the end. And then you will find that what you get is this ratio. And then, just to lighten up the lecture a bit, this move is called the slam dunk move. I don't know who invented it, but it goes by this name. So questions?
So if you have just that simple link, right? You do surgery along the solid torus. You glue to solid toric.
Okay.
So in that case, to compute the partition function, you just need to know that wave function.
I need to know the wave function and then the SL2Z, how the SL2Z that acts on
so
the...
given wave function to SL2Z, you get the...
Yes.
And it's...
So is this okay? I mean, am I going too fast or too slow or lag on? So I said that I mentioned that this surgery plus minus 1, 1 surgery doesn't do anything to a manifold. Let me just show you why. Well, let me show you what happens to this surgery. So by definition, let me just do the 1, 1 surgery. By definition, what happens is that this cycle is the A plus B cycle, right? Because I'm doing 1 plus 1, 1, 1. So I'm supposed to, what I need to achieve is that I want this cycle to become this contractible cycle after the surgery, right? So, okay, there's a bit of mental gymnastics required here. So, so how do you do that? How do you envision it? So what you do is actually you cut, look at this toral hole. You slice open this internal disc. So this guy, you slice open this cycle here, and then you slightly separate this disc which is bounded by this circle that you cut. Okay, so slightly separate them. Then do a 2-pi twist, put them together again. Okay, you see what happens is that if you cut that one open, then you do a 2-pi twist, which means you exactly bring this one all the way back to here, which means this cycle becomes this cycle. Okay, this does nothing to this 3 manifold, yet it does very interesting things to the links, to any links that goes in between. So let me. Okay, so let me suppose there is a line that goes through this hole here. Now, I said you need to cut that open, do a 2-pi twist, put it back, right? Which means what you have is that this guy in this process gets an extra twist along its axis because it is clear. Okay. Now, what's more interesting is that what happens when you have 2 links. After this surgery, these 2 becomes tangled, or something like that, because of this twisting process. So this was the comment I was making. By using this move, you can always so you first do surgery along a link that is linked, but you just apply this move repeatedly. You can untie these links. Eventually, they become links that are not linked. Okay. So, yeah, this is a long digression. Now, we have seen how to do surgery, but what is lacking is that we still don't know what is the wave function that we assign to the torus. Now you have seen that the surgery along the torus is the most important one, so we just need to figure out what's the wave function on the torus, and everything else is just pretty simple. Okay, so this will bring us to get the Hilbert space. We just need to do quantization, right? Let me clear the board. So we are leaving the surgery now, and last chance for questions.
So before we specify to the case of torus, can you just say in general when you have a three manifold with a boundary sigma, and you consider Chern-Simons as a theory on the manifold, what boundary conditions do you put on sigma for fluids?
What boundary?
What are boundary conditions for
Well, what you normally put,
connection
what you
on sigma?
you don't the boundary conditions that you specify the holonomy around cycles, because these will because on a two-dimensional surface, basically the Hilbert space is flat connections on that space, right? So you fix the holonomy around the cycles.
Well,
Then you
fix holonomy, but are there any Dirichlet-Neumann conditions on
The-
conditions?
the what?
Dirichlet or Neumann or any kind of conditions?
I think it's going to be fine if you just fix holonomy. Right. By the way, the torus has got two cycles, so you actually don't fix both holonomy, because these two holonomy are like the momentum coordinates. So you just fix one of them, the other is left free. When you know that from uncertainty principle, you fix the coordinate, momentum is free.
So you integrated the space of all fields with fixed holonomies. No,
Right.
nothing, no more restriction.
Right. We will do this actually. We'll do this calculation. Further questions? Okay. So finally, this is the first time I write on Chern-Simons theory action. So, to do quantization, we just, well, put the Chern-Simons theory on a two-dimensional surface times a line. And then, so what we do is that we can split A into A d sigma A into A t dt plus A perpendicular. So A t is this direction, the time. And then if you just plug in this splitting, what you will get is B2 sigma BT. Okay, so here we recognize
You have too many a's in this term. AT, A perpendicular.
yeah, AT and A perpendicular, and that's the only. So this B sub sigma is the ramp on this space.
Right, but you have AT, A perpendicular, the sigma, A perpendicular, right? Too many.
No, I don't. Oh, right. Sorry. Yeah. Okay. Right. Okay. So this term you recognize as the Q dot P term, and whatever this is it's supposed to be the Hamiltonian. But you see that in this special case, the AT doesn't get the time derivative, so it's just a Lagrange multiplier, which means your Hamiltonian is just a Lagrange multiplier. And from here, and we know that from this, we know that the symplectic form is going to be the PDQ term, right? So the symplectic term, form is equal to integral over sigma delta A perpendicular delta A perpendicular. So we will be just quantizing. Naturally, we have to mod out the gauge equivalence, which means we will just be quantizing the space of flat connection. Sorry, I forgot to mention that if you integrate out AT, this enforces the condition that this is a flat connection. Okay, so the quantization problem becomes thus that you quantize the space of flat connections with this symplectic form mod the gauge transformation. And okay, bad organization. I need to mention that in the previous list that I gave for the axioms due to Atiyah, I said I only restricted myself to the Riemann surfaces, but in fact everything can be repeated for Riemann surfaces with marked points, namely punctures. Here actually I'm going to do that. So let's try to figure out. So let's suppose sigma is S2 plus 2 punctured points. So the punctured points, if you think of it in physics language, it's just like charges. You put charges on it, and then you excite some flux lines. And then, so which means in the non-abelian case, they are marked by representations R and S, for example. And then we know that from basic PEV that if it's not equal, if S is not equal to the dual of R, then there's no way you can put any flux lines on it, because for any source you have to put a sink. If the source and sink don't match, you can't put any flux lines on it. Which means in this case, the Hilbert space is zero-dimensional. 0E. Now, if we do assume that S equal to R bar, then we know that basically what we do is that we try to decompose the tensor product of R and R bar into a bunch of representations. And out of this sum of bunch of representations, whenever you see a trivial representation, that means you can, so how many trivial representation you get in this decomposition is the dimension of the Hilbert space of this space. And then in fact there will be only one trivial representation, because if I assume that R is irreducible, then there will be only one trivial representation appearing on the right hand side. Yes?
So given a representation of puncture, how you define path integral, how representation enters into the path integral with puncture?
Yeah, so yeah, you just ask that for me.
Okay.
No, it's good. At least I'm not losing you. So if you do think of it as in terms of path integral and wave functions, what you think of. So in this case of course there's nothing to think about. In this case, what you do is, let's say, you just fill up this S2 with fill it up, and then you have these punctures. In fact, what happens is you just put a Wilson line in here, and then the Wilson line transforms in the representation R, and then because of the orientation issue, in this case it goes out, in this case it comes in, so you get R and R bar. So this is how it comes about. So this is how you should think about it. So you put a Wilson line in this solid ball and do the path integral in the interior of this, and then this gives you the wave function associated with the particular vector in the Hilbert space that I assign to this space.
Oh, but if I have several punctures, several representations, what Wilson lines I put?
Right, so you have different bases. So, for example, this is basically so you can put like this. So each way you put Wilson lines gives an independent basis. An independent basis for the conformal block. Actually, I guess you have already recognized this as what I'm doing is just conformal block stuff. So take this, take the Western model on this guy, and then the punctures are just punctures transforming R representation R and S is just I'm inserting the primary fields transforming R and S. Okay. Now if you have a bunch of these guys, there are let's see, you have four vertex operators inserted. Then your Hilbert space is just the dimension of the conformal block. So this is a valid conformal block. Namely, the dimension the dimension of the Hilbert space is equal to the number of representations you can put in here. Okay, and then the T channel is also a valid one. So let's say spin a half, spin a half. Then this you can get spin 0 and spin 1, right? So in this particular case, the conformal block is two-dimensional, and this one is also two-dimensional, and they're related by the S2. Okay. So other questions? So in fact, now knowing that the sphere with two punctures marked with R and R bar is one-dimensional. Oh, a trivial remark: a sphere without any puncture is of course one-dimensional. There's only 0 as the flat connection, nothing else. Okay, so these two facts pretty trivial, but actually they have very interesting consequences. Let me just show you what to do. I think I'll just show you what is the consequence of these two simple observations, and then we'll pick up next lecture. First of all, where is it? Oh, here. The sphere without any puncture is assigned as a one-dimensional Hilbert space. What does this tell us? So now let me pose the following question. I have two manifolds, three manifolds, and then by this pound, whatever it's called, I meant what I do is that this is M1. I remove a 3 ball here. This is a B3, I think. So also I remove another 3 ball here. Then the remaining portion is just some manifold with S2 as boundary. I can glue them together, right? So this is called the connected sum. So this symbol means connected sum. Now I want to just ask, is there any relation? M is equal to that. Is there any relation between this guy and So now, just according to the axioms of Atiyah and also the surgeries, if we want to compute this the partition function on this space, what we should be doing is that we take the Hilbert space which we assign to S2, and then there are two vectors in it, and 1 minus the ball, and 2 minus the ball. Then Z of this space is just given by the inner product. Right? That's the prescription. Now, I can always do the following. Assume remember, this is also a vector living in this space, which is one-dimensional. Let's assume that this is not 0. Then I can just write this as I can always do that because it's one-dimensional. I'm just sort of normalizing all the vectors according to the length of this vector. I can always do that, right? Now, let's just see what are these things. Well, this is, see, here we cut a B3 out of M1, then we put it back in. So it's this one, right? So the numerator is just Z of M1, Z of M2. Is that clear? And down there, I'm just gluing two balls in a trivial manner, which means what I'm getting is okay. And this is supposed to be the Z of the connected sum. Okay, it's quite simple, right? And I think I don't want to go over time too much. I think I'll stop here and pick up next time.
Any questions for Jump? questions.
When you, in the beginning, when you formulated these axioms, you formulated it as this, this parallel. What actually, what's the status of axiom here?
I don't think I can answer you that question.
Mathematician is trying to interpret what physicists are doing.
I mean, I suppose you could.
I mean, I sort of recognize this from different paper, but I never thought of it as axioms.
No, I don't think I can answer this question. It's a bit of a philosophical. What is your attitude toward path integral, and how do you understand it rigorously? I really can't.
But for T, it was a way of formalizing manipulations. So it's basically, in the way of building the functor from, this gluing and cutting, this what's called more Bordism category to, category of vector spaces. So it's important thing that you do certain things with vector spaces and you do certain things with manifolds. And then this operation should be mapped. So these guys, form what people call category. These guys form category, and there is a map functor, and this functor is TFT. So if you come with a map, doing these operations consistently, then you construct
these
it.
Axioms all came after Witten's.
They came, I think, more or less in the same time. They were presumably talking and trying to understand. But I think it's a way for a mathematician trying to understand what physicists are doing. But for people, they're just axioms, and then they can start to play. This piece of math becomes. Any further questions? If not, I thank John again.